Like till now, several times we use this word spinor. So just to make clear, so this word spinor, it was a kind of like a mathematical object used in physics now. Today in physics, we use the word spinor, but it was a kind of a mathematical object which belonged to a complex vector space, and it also somehow associated with the Euclidean space. And it has some physical interpretation definitely. So let's try to give a like overview what is the interpretation of spinor and what is the corresponding mathematical ideology we used in spinor. So based on the statistics, one was a bosonic particle, which is an integer spin, and we had a fermionic particle which is half integer spin. And in bosonic particle, with intermediating particle, or we call it sometimes force particle, gluons, photons. So this gluons for the strong interaction, photon for electromagnetic interaction, W plus minus Z. This was for your weak interaction. So all these are the spin 1 particle, and this is a vector particle. And also in a standard model, we had Higgs, which is spin 0 scalar. Interacting particle, all the quarks and leptons, which are the spin half particle. These bosons, those are the vector particle, which we will see in a moment what I do mean by vector. But those fermions, which are follow the spin half integer statistics, for those, what is the representation for those are spinor. So this is a thing we'll keep in mind. Now let's try to understand what is the spinor mean.
Okay.
So now when I'm talking about the vector, so let's start from this yellow point. So you start from here. When it make like 360-degree rotation, again it's come back to the original position.
Yeah.
So whenever we consider a vector, basically we define any physical quantity, either a scalar or vector. It is based on some transformation. Let's consider rotation is one of the such transformation. So when we make like 360-degree rotation of a given physical quantity, whatever it could be, if it is again returned back to the original position, which is having like some magnitude and direction, that physical quantity we can define as a vector.
Yeah.
And which is very well known to us. Now when we talk about the spinor, so at this point the spin is up, it's make one rotation. When it reaches to the 360-degree, you can see the spin is become down.
Yeah.
And to reach one more to the original position to spin up, it's need like one more rotation. So what a vector can do, after 360-degree rotation, this vector can reach up to the original position. But for the spinor, which basically initially a spin up position or spin down position, whatever you can consider, after 720-degree rotation, I mean 2 times the rotation what vector can do to reach the original position, spinor take almost 2 times of that.
Okay.
So this is also the concept which is called the Dirac bell trick. If you take a belt and if you make a rotation, and so it will like twisted. If we make one more rotation, you can see the belt is again come back to the original position.
Okay. But this is a mathematical object, right? Like we are just defining something that has this property, just like complex number. So there is nothing real about complex number. We're just saying like there are 2 portions, one is real portion and then the complex portion. Complex portion refers to like a phase and it refers to the angle in which it moves. But there is nothing like imaginary number. So it is just a mathematical representation. So the spinor over here, it's just another mathematical representation, right?
Yes, as I said in the very first slide, that spinor is a mathematical concept.
Yeah.
So, but later we use this concept. I mean, in physics, without mathematics, we cannot go further. So the concept of spinor, it was a kind of representation of some of the physical quantity or physical quantity, like which represent the spin. We understand why for spin we need this concept of spinor. If I consider a scalar quantity under rotation, it does not make any transformation. It will remain same. It will not make any change, right? But for vector, we need to make like 360-degree rotation. Then only we can reach to the original position.
Okay. So let's say one thing. Say this this one object, and then if I make one rotation, so if I just make one rotation, then it's like still it is the same view actually. The view is just the same. So this particular thing is just in the front. So if I make rotations, the view is the same. But in spinner, if you make one rotation, then the view will become like opposite, something like upside down.
Yes. Yes.
Right. So the question I have is like, so the reason why we study spinners is like these fermions, for example, which has half spin. Half spin, like we need 720 to get it to the original position. Spin one particles is like 360 we get the same position. Same like it looks like a vector. Spin one. Spin half is like we need like 2 rotation to get the same position. Right? Do we observe this physically? Like when I say observe this physically, what I mean by that is like, does the property of this subatomic particle differ when it is a spin up and spin down?
Yeah. So first of all, this the concept of spin is an intrinsic property. So it's not that we can observe the definition of we cannot visualize a spin, because it is something intrinsic. It is something that's the beauty of quantum mechanics. In classical physics, there is no concept of spin.
Yeah.
Because in whatever the thing in classical physics that we can visualize, but whenever we call something intrinsic, that is something by definition. It comes from a definition of the physics. So we cannot see the speed itself, but what we can observe the corresponding effect. Like if you remember how the spin was discovered by this experiment called Stern-Gerlach experiment, which is I think one of the first quantum mechanical experiment. What they observed, they had some magnetic field in between, some non-homogeneous magnetic field. When the beam of silver atoms was passed through that, then they get some structure or some splitting. And the splitting was not expected, but when they tried to interpret this splitting, that was interpreted based on the quantum mechanical intrinsic properties called spin. So to answer your question, there are many experiments nowadays going on where they study the spin polarization. So when you're talking about the polarization, it is similar to how the light is polarized. If I consider light, there's two kind of, one is left circularly polarized, right circularly is polarized, elliptically polarized. So similar to the electromagnetic wave polarization, it's also possible to study the spin polarization. So there are many experiments like Alice collaboration. They are very well known to do this study of spin polarization. So interconnect between this the polarization based on the electromagnetic wave and polarization based on the spin. And to interpret that in terms of spin, you need this spinner. So to just to concise answer of your question, that directly we cannot see the spin because it is by definition of the intrinsic definition of the quantum mechanics, but we can study the corresponding effect like the spin polarization, which is very well known in high energy physics, or the concept of spin polarization.
And spin is a magnetic property, right? Like it is affected by the magnetism. Like here in this experiment, the spin up is like attracted towards the south pole, and the spin down is attracted towards north pole.
In this experiment, this was coming because of the spin orbit interaction. So the orbital magnetic moment, they interact with the spinor component of the atoms, and that make this splitting. So the spin can interact with the magnetic field, but it's not really magnetic property. I mean, this spin is completely intrinsic properties of quantum mechanics, but the spin can interact with the magnetic field.
So a small deviation. Yeah. So just like the spin interact with the magnetic field, we are seeing the electromagnetic. That's again another interesting property, right? The electromagnetic photons. So they interact with the gravity field. We are seeing this gravitational lensing and everything. Just drawing something parallel actually, like so the electromagnetic particles, when they travel in space, and because of the space distortion of there is a gravity field, intense gravity field, and that it gets interacted That's why it's bending. Can we say like that?
One-to-one analogy, but yes, if we try to make analogy, then yes, true.
Like here we know it's interacting.
Yeah,
Here
so
we
in
know
this case, yeah, in this case, at least in this example, the spin, which is one of the quantum number, we can say, better word to use the quantum number of a given state,
or quantum number.
or quantum state, which is a kind of a good quantum state, and which can, what a representation of this spinor state, a spin state that can interact with the magnetic field. So if you want to make this analogy, this photon which is quantum mechanic or electromagnetic intensity property, yeah, that this analogy could be possible.
Yeah, but there are two interpretations there, right? The gravitational lensing, there are two interpretations. One interpretation is like the space itself is distorted, so the electromagnetic particles are not interacting with the gravitational field. They're just following the space. Since the space is distracted, we are seeing this gravitational lensing. That is one interpretation. Another interpretation is like I'm thinking like this one, where the space is not getting like bent or anything like that, but the photons are getting interacted with the gravitational field, and then hence we are seeing the bend.
It's the interaction may or may not be like one-to-one analogy, but yeah, if we can imagine on that way, it's possible to make this kind of analogy also. Complete this story. Why this spinor is important? So this spinor, so there's two possible state we sometimes define. One of the state which is called the physical state, I mean the state we are deal with, which is very well known to us. We call it physical space. And if if I just consider this object which is spin up right now, if I make like 180-degree rotation in the physical space, the tip of this spin, it will be down. So this is kind of our physical space. But when you're talking about the abstract space, where the quantum mechanics is very, very good to tackle with, to handle with, and if we have two state alpha and beta, I mean, when I talk about state, I'm representative of the particular state alpha and beta. If those are based on the postulate of quantum mechanics, if we have two states, this is supposed to be orthogonal. But that means they must be mutually exclusive. So if it is true, if a spin that could represent that orthogonal state, the spin up and spin down, if that is represent this orthogonal state, then what is the difference between a normal vector and the spin, the corresponding spin representation? So this spin, as I said, the spin up and spin down, these two, by definition of this quantum mechanical abstract space, they're supposed to be orthogonal. That means the spin up and spin down, they should be like 90-degree rotation. So to get what exactly we can think in the physical space, I mean, if I want to make this up and down in abstract space, we need to make a 90-degree rotation, but in physical space, we need to make like 180-degree rotation. That means there is something called double folded theory. That means if we want to reach from the abstract space to the physical space, we need this double folding. That means we need to make like 90-degree to 180 degrees.
So what do you mean by rotation? Like rotation is we are talking about mathematical property, right?
Yes,
so
yes.
we'll never observe a electron in like in an in-between state. We'll never observe like that. Either we'll observe in like in the up state or spin down state. We'll never observe in between state. Or like here we are saying the physical space. A physical space, we are saying like if we rotate 180-degree, it like we are going from spin up to spin down. But my question is like that in reality we don't rotate the electron at all. Like there is no way we can do that. It is just an like it is just an observation. Observation is like there is an electron which has a property of spin up. There is an electron which has a property of spin down. We are not able to rotate. We cannot rotate a electron that is a property of spin up into spin down. We cannot do that.
What I mean by rotation here, so I just try to make an analogy first of all. So it's not really that I am rotating the electron to get this spin up and spin down. So when you're talking about this rotation, actually you're thinking about in terms of angular momentum. So I'm not talking about angular momentum. So here I'm just trying to give an analogy. So when you're talking something up and something down, so that means you are thinking in terms of angular momentum. So here I am not talking about angular momentum. So I'm just trying to make an analogy why these spinors are similar. What we are so I'm just trying to give you a mathematical approach to understand why the spinor that are good to represent the spin. Okay, so again I'm just repeating that the spin is an intrinsic characteristic. So we cannot think something the spin is the electron is rotating up and down, that's why you get spin up and spin down. The thing what we were talking about, something up and down, it is in terms of angular momentum. So so angular momentum is also a quantum number, or basically a good quantum number. Spin also a good quantum number, but they're some completely different, because the spin is represent the intrinsic property. It's not something because of rotation. Okay, definitely in this picture when I'm showing you is just to give a representation. Something is rotated, something is going up and down. This is not true. I'm not saying that spin is something up and spin is something down. It is completely an abstract concept of spin. I mean, that's why the abstract algebra is so good to explain this concept of spin, because the concept of spin is itself abstract. I mean, it does not have anything like something which we can visualize. Like the picture I'm showing, it's completely nonsense. It's not ideal, but I'm just trying to give you a kind of overview how the mathematically. I mean, this is completely mathematical concept, right? But I am just trying to make an analogy with this mathematical concept with the physical idea. So you're completely right that it's not what I am talking about, that it's not that we are rotating the electron by hand to get the upspin and downspin, because to getting the spin up state and spin down state of a given quantum mechanical state is completely intrinsic, or completely come from the definition of that state. Is not because of the electrons rotating up and down. So in the next slide, when I was talking about this abstract space, so this is again kind of assumption or kind of postulate of quantum mechanics. So what I am trying to show in the left picture, when I'm talking about this spin up or spin down, just let's consider at least for the physical space. Can you see this pin?
Yeah.
So when I consider the spin up, just I mean the top tip of this spin is on the upside, and if I make like 180-degree rotation, the tip of this spin is down. So that's what I'm meaning in the physical space, because in physical space there's nothing we can think of spin, right? But I just want to make an analogy so that we can understand how this analogy go at some particular meet at some point, so we can make some conclusion. So in the physical space, when I consider spin up, so at this point, let's consider this tip of the pin as a spin up, okay, and tip of the pin is spin down. So if I want to reach to the spin up to spin down, I need to make 180-degree rotation, right?
Yeah.
So then what I'm trying to go further, okay, the concept in the physical space is very well known to us. Let's try to understand the same concept in the abstract space. That means in the space of quantum mechanics. Okay, so there's a specific rule, or not rule, or assumption in quantum mechanics, which is called Born's postulate. Born postulate that if you have two states, alpha and beta, if that is a quantum mechanical state, I mean whatever the representation of the quantum mechanical state, if it is spin state, they will be mutually orthogonal or mutually exclusive. That means they are orthogonal to each other. So if I want to represent a spin state which is true, which is measurable and not measurable, which is valid physical concept, that we can represent a spin state. And if I consider two spin state, one is for spin up state, spin down state, that is based on, again, from the statistics and quantum mechanics, then they're supposed to be orthogonal to each other. Okay. Now again I go back to my intuition, or just to make a kind of analogy with this pen. So when I set the spin up in the physical state, if I make 180-degree rotation, I can go to the spin down state.
Yeah.
Now, when I go to the abstract space, I am in the spin up. So by definition of the abstract space, my spin down supposed to, if I make a 90-degree rotation, it's supposed to spin down.
Orthogonal, yeah.
Because of the orthogonality of the quantum mechanics.
Yeah.
So what is the connection between physical state and abstract state? So to reach from abstract space to physical space, you need to make like a twofold rotation. I mean, you need to make one more rotation, then you can reach to the physical space. So there is also something called twofold theory, which is very, very well known in topology. So I think in quantum field theory, in high or in particular physics, the concept of topology is very. I mean, this is one of my best favorite subject, topology. I mean, this is something completely start from the abstract, but the way it able to explain the physics, the concept of physics is extraordinary. So this is complete topology.